let's start. So welcome everyone to the fourth edition of this Twitter Spaces. Thanks everybody for coming. For those who are here the first time, I'll just say a few words, about what this room is for, right? So this is a regular bi-weekly meeting. We mostly focus on low-level performance and everything related to that. So how to analyze and find performance bottlenecks in your application. We talk about hardware, operating systems, compilers, high-performance libraries, programming models, and so on and so forth. So performance is a huge topic, right? And it's very complicated. Well, that's great that we have great folks from different backgrounds, coming from different industries. So I really value having such a, let's say, diverse set of engineers. So but I primarily consider it as a place for sharing ideas. This is really the primary goal for me to organize those Twitter Spaces room. Yeah, and for me personally, it's been a great place to learn from all of you guys. So and I want to keep the mic open. So feel free to request the mic if you have something to say. While I encourage everyone to participate in this discussion, like please be mindful about it, right? Okay, so joining us today, Mark. Mark is a senior performance architect specializing in low latency C++ and Java environments. Mark has more than 15 years of experience in architecting trading platforms and minimizing latency. Mark currently works at WH Trading Company, and also Mark leads his own performance engineering consultancy firm called JabPerf. Mark, welcome. And I personally, would like to thank you for helping me with my book. So Mark provided a valuable experience throughout many, many stages of the writing of my book. So I really appreciate it. Thanks, Mark, and welcome.
Thanks a lot, Dennis. I'm sorry, my phone started ringing, so you cut off. So I don't know what I missed. But the last thing I heard was that I helped with the book, but I didn't hear anything after that. So I had to turn off my phone, the ringer.
That's fine. Yeah. So Mark, so we're talking about today about high frequency trading. So this is the area of your expertise. So Mark, you worked in HFT for quite some time, right? So while I assume the most folks here know what the high frequency trading is, can you just give a
I'm sorry.
Sure. Yeah.
Dennis.
Yeah.
I need to rejoin. Just a second.
Okay. Sure. Yeah. All right. So hey guys. So while we're waiting for Mark, I want to again say Happy Father's Day to all of you. If you are fathers. Okay. Now we have Mark back. Hello, Mark. Mark,
can you hear me?
Are you here? Yeah, we can hear you.
Okay, great.
Yeah, so can you just give a short overview of what high frequency trading is?
So high frequency trading is the umbrella term that the industry, when I say the industry, I mean just the general media, the mainstream media. It's like an umbrella term that people use for algorithmic trading. So instead of actual traders being in the pit and doing trades in person on the trading floor, it's done all by computers, where the trading algorithms are programmed, usually C++, some places use Java, but the algorithms trade automatically. And so different firms use a variety of different strategies, but mainly the companies that I've done performance engineering for, they've been market makers. And what a market maker does is they'll trade in a specific financial instrument, whether it be a stock, a future, an option, and they'll quote prices on the market on both sides of the market. So they'll offer to buy and offer to sell for the same instrument. That's making a market. And so what they hope to do is to make a profit off the spread. So where the latency issue in that whole situation comes up is the market moves all day. And so whatever price you quote on the market, if the market moves in a certain way, or there's some kind of news announcement or something to that effect where you need to adjust your pricing, you want to be able to respond to the signals fast enough so that when you see this market event, you can shoot out your message to the exchange to say, hey, I want to modify my quote, or I want to cancel my quote. You want to be able to do that as fast as possible. So the terminology for that is tick to change. So you get a tick, which is the signal from the market, and then you want to send out a change as soon as you can execute your trading algorithm based on that tick that you came in with. So that's where the low latency issue, that's the low latency issue that I'm trying to solve for trading firms that I work for.
Cool. That's great. Yeah. So, but how did you start working in Hft?
Well, it's interesting because my first HFT job was in 2009. Before that, I was working in general industry. So I had worked at large firms like Goldman Sachs or Encyclopedia Britannica or Blue Cross Blue Shield. So I was doing, I came from an engineering side, whereas most of the performance engineers that I know, they came from the development side. So I was a Unix Linux engineer, and then a Cisco engineer, then an Oracle DBA, then a SAN administrator. So with that varied experience with all the different infrastructure that makes up a platform that or a business platform, the way I saw it is that I had a couple of ways I can go with it. I can specialize in performance, or I can specialize in security, because in both of those avenues, you have to have a wide purview, and you have to have a wide, broad base of expertise in order to do that job well. And so what I found was performance was really what would get the CTO's attention. Whenever you made some kind of performance improvement, the CTO would know right away, and they would know your name down the halls. Whereas security was kind of like well, we need to have it, and nobody really thinks about it unless a breach occurs. So it wasn't very much viewed the same way in the industry. So I chose performance, and that performance track got the attention of one particular trading firm, IMC, and they reached out and asked if I wanted to interview for the company as a performance engineer. And so that started my journey into algorithmic trading.
Yeah, that makes sense. Yeah, great. So, but so what it takes to build, an HFT system? Like, for example, can I build it myself? Like, if you are doing it, like, from scratch. So how hard it is to to build this sort of system?
Well, the thing is, there are people who do it solo. There are people who, I mean, small 2 to 3 firm people. I mean, two or three person firms that do trading on their own. The hard part is getting the kind of equipment that you need, and to getting it into the data centers where you need to be. Because if your algorithm is very latency focused, then you want to have your equipment in the same data center where the exchange is house their matching engines. And so that's the whole thing. The colocation, the cost can be pretty high, pretty steep. So what you'll find some traders do is, like, some traders, they're pretty successful and they do it on their own, but some will actually have some kind of contract with a larger HFT firm to use their platform and execute their own trading strategies on the larger firm's platform, because the larger firm, they have the kind of capital where they can get that kind of infrastructure, where you can get the kind of low latency benefits that you need for a lot of trading algorithms. But it's not so much that it's hard to do, it's just expensive to do.
Okay, but if I were to to build one of those systems, like can I expect to make money from it? Or the big companies will eat all my lunch?
Well, that's another misconception about HFT, because the way the media makes it seem is that every trading algorithm, it's based on having the lowest latency possible. If you're not first, you're last, basically.
Right.
That's not every trading algorithm. Like there's a whole class that doesn't require the very lowest latency, of like tick to trades in the hundreds of nanoseconds. That's not every algorithm needs that. So there's a wide variety based on whatever your strategy is, and based on whatever your signal is, based on the kind of back testing you do and the signal that you're looking for. If you have a larger time scale, you can do it. You can make a lot of money on your own, and there are people who do that. But it's such a wide topic. I mean, the variety of algorithms that you can use and strategies it's a very big topic. But where you fall in that spectrum, based on where you fall in that spectrum, it depends on that, whether you can make money or not being solo and not having a whole lot of money behind you like you can with if you signed a contract with a larger firm.
All right, makes sense to me. Yeah, but what about machine learning? So does machine learning have its place in algorithmic trading? Like can you envision any like machine learning algorithm that will be capable of making a decision like when to buy or sell?
Well, there's a lot of back testing that happens in the trading industry. So there's a lot of infrastructure set in place where you have quants that we hire that are experts in math and statistics, and they build these models upon which we base our strategy, our trading strategy, in our pricing. So that's like where you get a lot of the secret sauce for some of the decisions we make. That's not in that kind of processing is not in the critical path. That's something that happens on the back end, and you get that once, and then you adapt to those pricing levels throughout the day, like up or down a few ticks or whatever the case is. But there's a place for rigorous statistical analysis with the back testing infrastructure in trading and companies. And now, when it comes to that area with the back testing, I've done some of my work is with that, so they can get better performance out of the hardware that they purchase. So they can get, for instance, better vectorization and things of that nature. If they're using specialized hardware like GPUs or FPGAs. But the majority of my work is in the latency sensitive aspect of it, where you want to get the tick to trade and tick to modify and tick to cancel to the lowest levels possible. So for instance, if you want to work within the strategy groups that do tick to trade within hundreds of nanoseconds, then you're talking about FPGAs, right? You definitely have to do it on a hardware level. If you're in the single digit microseconds, then that's when you can do it in a general purpose CPU, like an Intel or AMD or something to that effect. So that's
cool.
primarily where I spend, I would say, 80% of my efforts.
That's great, and we actually will get back to that. So I think this will be a really cool area to discuss. But so for the moment, let's go let's go here. So you wrote actually a few articles about shifting left, right? So shifting left performance engineering. So, and I think that HFT, is a great example why it may be critical, right, for a success of the project. Like, because if you don't like design your HFT algorithm like with performance in mind, right, everything can go badly wrong at the very start, right? So tell me please, how do you shift left on performance testing in HFT? Do you have any examples, any specific steps one can take?
Yes, well, for one, a lot of the discussion around shift left performance in the industry, when you read these different articles, is basically about, because everybody's now onto this continuous integration, continuous deployment pipelines, where you the minute you check in some code, you're running the unit test runs automatically, and you're getting direct feedback quickly, so that it's not too far down the pipeline before you know something has happened. You're not introducing regressions in the production. So shift left performance is traditionally meant to put performance within that CI/CD pipeline, not just functional unit tests, but actually performance unit tests and performance integration tests within that pipeline, so that the minute you check in some code, it runs automatically. That's in contrast to how it's traditionally been done, where you just have the unit test and integration test on a functional basis. It goes out it gets handed off to the QA guys, and they kick the tires on it for a little bit, and then it goes out to production. And then that's the first time anybody realizes that there's a performance issue. Now that's a worst case scenario. Another case is, in the past, for firms that were a little bit better than that, they would have performance engineers only at the final stage, right before it was going to be deployed into production. And then they would do all the performance testing right at that final stage. This is after all the different sprints that have happened, where now the developers are on to something else. If a performance issue comes up now, they have to do some research to figure out what commit was actually involved with whatever the performance engineers found during their load testing. So it can be a big hassle and a lot of confusion in that way. So shift left performance is talking about actually putting the test within the pipeline, so the minute the code push goes in, you get immediate feedback and developers know exactly which commit caused the performance regression. My take on that, in the article that you reference, is that that's not shifting left enough, because there's been a lot of studies, a lot of empirical studies. As a matter of fact, there was one from last year. I think it was May of 2020. Andre Bondi was one of the researchers, but it was about 10 other researchers on that project, where they did an empirical study of a lot of open source projects and researching the kind of performance issues that occurred. And what they found was that 33% of those performance issues were due to architectural or design issues. So things that had to do with decisions that were made before even the first line of code was ever written. So my take is, the way shift left performance is spoken about now is not far enough. You need performance engineers in the architecture and design phase, so that any kind of anti-patterns in the design is caught early on, before any code is written. So that's my view on shift left performance. But I hope that answers your question about the way I see shift left performance.
Yeah, that definitely makes sense to me. However, so you said like that 33% of performance issues can be prevented, right? So if if it would be architectured and designed properly, but what are the specific examples that you can provide? So for example, so how deep enough you should really design, okay, well for example, you can choose data structures and algorithms properly, that's fine, but How about other, low level things like should you design your architecture with hardware in mind, or anything like that? So, do you have any sort of specific examples how you can shift left performance engineering?
Well, hardware can go into it, but it's mostly okay. I'll take an example of I'll take one example from my own past experience where the way there was a CQRS, a command query. I forget what it stands for. Command query read something. I forget what CQRS stands for. But anyway, the system was based on it had a database connectivity portion to it, and the way the query was set up was that the anti-pattern, the performance anti-pattern that refers to the way this system was designed is called the Securities treasure hunt. As a matter of fact, Connie Smith and another researcher he's escaping my memory right now, but they wrote 3 research papers on the top software performance anti-patterns at the design phase. And one of them is called the Securities treasure hunt, whereby you have to go to the database to get one piece of information, and then you come back, and then you make another query based on that information, go to the database to get that information, and then you go again and back and forth. And so there's all these hops just to get the information you need to do to process, to continue processing on the middleware end. So that was one particular thing that I can think of from my own past where that architectural decision happened, where we had to undergo a little bit of extra work on the that probably could have been avoided had performance engineering been included in the architectural design. So
Of the database, that's right. Of the database, right?
Exactly. That whole query, that query setup. Perhaps if they did some kind of adapter pattern, so that if they chose to put the database separate from the middleware, then you don't have all these network, because that really extends the latency if the database is separate from the middleware, which is probably how you want to do it if you want to scale. So you have all these network hops, and even if it's co-located with the application middleware piece, just that constant back and forth, that latency that you get, as opposed to if you just intelligently denormalize in a certain way that doesn't hinder other queries, then you can get better performance. And that's the decision we end up making. We kind of denormalized the data that was involved with that specific work function, and we achieved a huge performance increase. But because it was an architectural design issue, it took more time to get that change in place than it would have had we been included early on in the process. This is in contrast to some of the typical things we talk about in the book, the book that you wrote, where you can do localized performance improvements based on code profiling, where you can change the way a loop is constructed, or you make a few changes here to maybe using a stud vector instead of some other data structure. Those type of things, you get a huge win from that, and you don't have to have as much interaction with so many different people in order to get that change in. But it also takes a whole lot less time for those kind of changes. But if it's an architectural change and you find out later in the process, then there's a lot of communication overhead that has to happen. There's a lot of coordination that can slow the process down, and it can be a big headache. And the tendency is with larger companies, they tend to want to avoid that. If they see it's going to take that much work, that much inter-team coordination, they may try to kick the can down the road and just try to trim fat off the sides. And that's when you end up getting this mess of code that people are doing these workarounds, and the code gets messy and unmaintainable over time. So it's a lot of issues can be avoided if performance is taken into consideration at the architecture and design phase.
That's true. Yeah, and it is actually somewhat opposed to the famous quote from uh, from Knut, right? So he's like, he said that, a premature optimization is the root of all evils, but on the other hand, like, not thinking about performance at the very beginning can as well cause as many troubles, right, as premature optimization. So
yeah, and
that makes sense to me.
the way I've always considered that quote, like there's actually been a paper written about that quote and the way it's been misinterpreted, but the way I've always read that quote and the way I believe that it was originally intended is that, doing micro optimizations early on and thinking about doing those kind of things before you've actually done the real hard work of profiling and seeing where you get the bang for the buck. That kind of premature optimization, that's the real scourge. But thinking about sound design, sound performance design, making sure that you're not introducing any obvious patterns at the beginning, I think that's always been something that was recommended.
Right. Yeah. Okay. So let's talk about benchmarking. So how do you measure performance? And I assume it's not in unit tests, right?
Right. So for me, every firm I've ever worked for, I've set up a lab, an R&D lab that mimics production. So I would have, so basically when you think about a trade setup, you get market data from the exchanges, whether it's Chicago Mercantile Exchange, the New York Stock Exchange, whatever the case is. You're getting market data in the form of UDP multicast. And in this UDP multicast, that's where you're getting all the market information about what the book looks like, what's the bid, what's the offer. You're getting all this information from the exchanges, and you ingest that into wherever your trade application is running. Your trade application ingests this UDP multicast data. It looks for signals that it finds attractive or that it finds interesting in order to make a trade or to adjust the quote or whatever the case is. And after doing that processing and seeing that signal, then it sends an order, whether that be a quote cancel or a trade or whatever the case is. And you want to make sure that that happens as fast as possible. So in order to set that up in a lab, you basically set up a server that can replay market data, which is pretty easy because the market data is UDP. You can just capture that data and then replay it with TCP replay. And what's great about TCP replay is that you can replay the market data at the same rates that it was captured at. And what I mean by that is, market data, it comes in at it doesn't come in at a steady rate, right? If some kind of market event occurs, you can get a huge microburst where all of a sudden you get a flood of packets, but then most times maybe it's only like 1,000 packets per second. But then during this brief microburst, you're getting like 1 million packets per second. So what you want to avoid is you don't want to capture market data for a given day and then replay it at some steady average rate, because then you're giving yourself a false sense of security if you do trading that way. You want some kind of infrastructure set up where you can replay it faithfully to the way it was recorded. So so for certain rates you can do that with TCP replay. Other firms, if you want to do it, if you want to be a real stickler for it, then you use hardware replay devices like Ixia and Spirent and things of that nature. So yeah, so you have the infrastructure that replays the market data. You have a server set up that's running your trade software, and then you have another server set up that functions as a fake exchange where you can send your orders into. So, and then you have your infrastructure where you take timestamps on the network all along the path. So you know exactly how long everything takes. And that's basically how you set up your R&D lab. So you can do all kind of testing, and you can do all kind of what if scenarios in that lab safely, and then you can roll out into production once you've done enough testing.
Yeah, that's great. And so this is how you measure latency, right? So you record the timestamps on the packets, right? And this is your latency, correct?
Yes. And so yeah, and then you make sure you have accurate time stamping. So some firms use PTP. Other firms, if they need, you need PTP if you want sub microsecond synchronization accuracy. If you want even less than that, if you want even sub nanosecond, you use White Rabbit, which uses a special kind of Ethernet, synchronous Ethernet, and you can get even tighter time synchronization. But then you have some kind of device that taps the network, so you're getting timestamps at every level where the packet arrives. So you know exactly which, if you're getting the latency in the network devices, you know exactly that from the timestamps you have. If it's actually at the trading application itself, you know that exactly from the timestamps you're getting from that centralized logging. So it's pretty precise.
Interesting. Yeah, it's really interesting. So let's talk about the software and the hardware stack. So what are the challenges of HFT systems? Like in HFT you essentially you have to be quicker than everyone else, right? So what are the challenges here? So
well, the challenge is that in performance, and I noticed this before I got into HFT. If you look at every document or every best practice article written about performance, every server that's manufactured, every network device that's manufactured, everything is geared toward throughput. So, I mean, think about it. It's like the way TCP is set up, it's like, the TCP nagling and delayed at. These are things that optimize your network throughput, but they harm network latency. On Linux, the scheduler is great when you want to cooperate among a bunch of different processes and you get a fair amount of CPU among all of you. But it's anathema to anyone who wants to do low latency, because you never want to schedule. You want to be pinned to a core, and you want to remain on that core, and you don't want anyone else to interrupt you. But by default, that's how Linux comes out of the box. It uses the CFS scheduler. It has a default setting, and unless you take pains to make sure that you don't schedule off your core, then you're gonna have these latency hits. Think about network cards. By default, many of them come with interrupt coalescing. And the reason for that is most people don't want to get an interrupt on the CPU every time a packet comes onto the NIC. So the way NICs work by default is that they'll take up a bunch of NICs, and after a certain threshold, then they'll send an interrupt, and then the kernel will come and process all those packets in one big batch. And then that way you can get a lot of throughput, but you suffer latency, because if you needed to know exactly when that first packet came in so you can process it, you're being harmed by this interrupt coalescing. And that's the general theme of every kind of equipment that you're working with, any kind of general purpose equipment that you're working with. You're fighting against the default configuration for throughput. So that's the challenge that when it comes to HFT. I've had to think, when I first transitioned into the industry, I've had to think about things that I never ever had to consider. people think about like on these new sockets that come out, or these new CPUs. So Intel Ice Lake, Skylake had 6 memory channels per socket. Ice Lake has 8. AMD Milan has 8. And so that's great. People think, oh, that's great. I'm going to have so much memory throughput now. I have so much bandwidth available for memory. And that's going to be great for memory throughput. So that's going to be great for performance. But what if you're a low latency shop where you're not doing a whole lot of, you have one application on a box, and it's not using memory haphazardly. It's using very sound data structures like a stud vector, or ring buffers. So it basically uses memory in a sequential fashion that memory likes to be accessed in. So you're getting really high cache rates, and you're not really memory bound. So do you still want to follow the guidelines of populating your memory DIMMs in every channel on the CPU? No, you don't, because even though you'll get the highest throughput that way, and you'll get the highest loaded latency if you populate a DIMM in every memory channel, if you don't use even a fraction of the memory bandwidth available, you're going to actually get a latency hit by having the CPU, what's the term, interleave across all those memory channels. There's a performance hit to memory interleaving across the socket. So you want to have as little amount of memory interleaving as possible based on what you need, and you'll get the lowest latency. So it could be the difference between 20 cycles, whether you interleave across all 6 or 8 channels, or just a couple channels. So these kind of things, you don't really think about that unless you're in the HFT industry, because you'll just follow the vendor guidelines and say, hey, put a DIMM the equal size in each of the memory channels on your socket, and you get the best memory performance.
Interesting. Yeah. So how do you solve that? So you just go with one socket and one DIMM?
Well, it depends, right? Because and again, of course, with performance, systems are so complex. There could be, I can have a hypothesis of what I think will be great for performance, and then I'll try it out, and it behaves nothing like what I thought it would be. And I don't know if you saw that video. This is like a CPPCon talk that Alexander, I forget how you pronounce his last name, Alandrescu or something like that. Okay. You know what I'm talking about, right?
Sure. Yeah.
Yeah. So he gave a talk about how he was trying to improve the performance of a certain sort, and he used all kind of sound reasoning about how this data structure will improve performance and how this one would. And it's like, oh, this one will actually work better because it will have fewer cache misses. But then when he tried it, he got worse performance. So it's like the whole talk was so entertaining, because just trying to use your intuition for performance is folly. You're just going to send yourself on a wild goose chase. You have to measure everything, and that's the only way you find out. So as far as the number of memory channels, you have to measure. The only way I would have known, I wouldn't have even thought to consider about the latency impact of memory interleaving unless I had actually measured it. And that's how I came to that conclusion. But it varies, right? It varies based on the kind of workload. If you're on a trading application that's reading a bunch of different market data for a whole lot of instruments, and you're getting a certain level of traffic coming in, and your data set is large because of the kind of computation you're doing, or whatever the case is, maybe your memory bandwidth usage is different in that scenario. It all depends.
Right. So are there any ways how you can dynamically adjust, like you can, like, for example, disable memory channels? Is there a way to do that on the fly, or no?
I don't know if that's the case, because it seems like what I've noticed is that the minute you put in an extra DIMM, I mean, well, you can in the BIOS you can disable interleaving in the BIOS,
Right.
or you can enable it. So as far as if there's some kind of MSR that you can set, I don't know what that MSR is. And now I've been surprised about the number of MSRs that are available to toggle certain features off and on. It's kind of amazing, especially on the Intel platform. I've only recently found out about how you can actually increase the size of the cache that Intel Data Direct IO will use based on the MSR. Before, all the literature said that it was unconfigurable. It's like it comes as is, but actually people have figured out what the MSR is, and now you can actually adjust that. So whether there's an MSR to enable or disable memory interleaving during runtime, I'm not aware of it, but I wouldn't be surprised if there is.
Okay, yeah. So, so Mark, so I actually, so there is a joke about HFT that, that folks in HFT think that the speed of light is too slow.
Yeah, it's true. It's very true. And it's funny. I mean, I know like a lot of people who aren't in the industry, you probably hear news about microwave, everybody using microwave and HFT. Yeah, we're trying to get close to the speed of light, and we're trying to surpass it if we can find that out. But yeah, it's an arms race basically.
Yeah, that's great, and I actually like that. That really the level of optimizations really spans all the layers, like all the hardware layers and software layers, like all across the stack. So that's really beautiful. So
yeah, it reminds me. It reminds me of one time I was interviewing someone who was coming from outside of the high frequency trading industry, and he was trying to join it, but he was a performance engineer somewhere else. So I asked him to tell me about a performance issue that he was proud of that he had solved. It's just so I can hear his line of thinking. And he went into this whole discourse about how he tuned the TCP stack for some application. And it was weird. Like one of the guys who was in the room with me, one of my colleagues, while we were interviewing, he had this puzzled look on his face because he had only worked in HFT, my colleague. So he was just wondering, why would anybody bother with the Linux kernel networking stack? It's like everyone bypasses the kernel stack. It's like, I don't want to hear this. But I was letting my colleague know, it's like, just let him finish the story, because it's not about what he was doing. I just want to hear his process and how he thought about performance. But no one in the high frequency trading uses the kernel networking stack. I mean, it's so much latency involved with that. You have to bypass it. So I just thought that was a funny story about high frequency trading.
Great, yeah, it's interesting. So let's first talk about hardware stack, okay? So what type of hardware is used in Hft systems? So like, is it CPUs, FPGAs, or some kind of a mix?
Oh, it's definitely a mix. And it's based on the kind of strategy that you have, right?
And the trade-offs, right?
Huh?
And the trade-offs, right?
Yeah, it's all about trade-offs. There are no solutions. It's all trade-offs, right? Because there's certain algorithms that require more real estate than what's available on prevalent FPGAs, for some of the more complex algorithms. But if you have a simpler algorithm that can fit in the real estate offered by an FPGA, and you can find someone who can program an FPGA, then that's where you can achieve those tick to trade latencies in the hundreds of nanosecond areas, like 100 plus nanoseconds. But for the most part, if you're not on hardware, if you're not trading on FPGA, then you're trading on general purpose CPUs like Intel chips. They pretty much own the market when it comes to HFT at this point. I know AMD, they're trying to make inroads, and they've been calling a lot of us to let us know about Milan 3 but right now the incumbent is Intel for the general purpose CPU.
Okay. Yeah. So you already started talking about that. So like that the out of the box hardware is not designed for latency. It is designed for throughput, right? And the same goes for the CPU, right? So in CPU we have like a whole bunch of cores that you probably don't need, right? So for latency. Let's talk about that. So how do you like really tune your and let's talk about CPUs now. So how do you tune your CPUs? Like do you like disable some cores? Like do you disable like simultaneous multi-threading and stuff like that? So
Yeah, so there's a standard cookbook that most guys in the HFT understands. Like you disable HFT. There are certain people who think that, well, I don't know if they think that anymore, but there used to be a line of thought that, well, I'll leave hyperthreading enabled just in case I need it, but I'll just pin one thread to one of the siblings, and I just won't use the other sibling. And they thought that'd be good enough. But of course, I know you know this because we worked on your book and everything, but hybrid threads, there's certain parts of the core that are dynamically shared, but then there's some that are statically shared. So just having it enabled, you're gonna reduce the resources that you have, the core resources that you have, just having it enabled. So it's better to just have it disabled right out of the box, so your thread can use the full processing capabilities of the core. If you don't need all the cores, Intel will give you these turbo tables to let you know that based on what kind of CPU speeds you can achieve based on how many active cores are available in the socket. So there's a threshold of sockets that allows you to get the highest CPU speed. So those are some decisions that can go into the process of whether you want to start disabling cores or not, but it all depends, right? Some people will just buy CPUs that have just the precise a number of cores that they need for the application. And so really then that whole decision process is not even a consideration anymore. What else? Certain things that are enabled by default are like C states and P states and power management. As CPUs get faster and there are more value added pieces that are added to a socket, so then the thermal threshold, the thermal envelope gets to a certain point that manufacturers, they have to build in these hidden these hidden power management and thermal management aspects to the CPU that you may not even be aware of. So that can be a real challenge to make sure that nothing on the core or the system as a whole is thermally managed, or power managed. You want everything to be running at the fastest speed possible, and you just ensure that you have the best cooling in your data center, and you're taking care of the thermal envelope and the power envelope on your own. You don't want any kind of variance imposed by the BIOS or by the CPU. So when you think about it, I mean, if anyone can go onto their BIOS, on their server BIOS now, and just look at some of the selections of what aspects have power management. Your PCIe has power management. If you don't receive a packet from your NIC for some span of time, your PCIe lanes can go into power saving mode. So then the next packet that comes in, now you have to wake up the PCIe lanes and then incur that kind of latency. And it's bad enough that PCIe incurs the latency that it does on its own. But then you have to come out of a sleep state or a low power state. Now you're really talking about some latency. right? DRAM itself, DRAM has refresh levels, cycles that it must go through. All DRAM, all dynamic DDR RAM has to go through refresh. So I remember this one scenario whereby we purchased a new system. I believe it was during the Westmere days. I can't recall, but the manufacturer sent us the system and enabled opportunistic self-refresh by default. And what that does is, if you don't access a specific DIM in a certain amount of time, then the DIM can decide, hey, I'm going to use this to start doing refresh on my own. And so it'll go into a low power state and start refreshing the cells on its own. Next thing you know, your application needs to access that DIM, and now it has to wake up out of that refresh state, and then so it can service your request. So we noticed this in our latency numbers, and we were trying to figure out, okay, where is this happening? It's like, so we had to go back and forth with the server manufacturer first, and then we got Intel support or engineering on the call, and we were having these war room chats where we figured out it was opportunistic self refresh on the DIM itself. These are things that, you know, I never had to think about before, but you become highly sensitive to these issues when you're talking about low latency.
Yeah, that's interesting. So actually, by the way, so are you using some, some kind of, automatic tools to, to tune your CPU? Because so I actually know that, for example, Intel release to its customers the automatic tool that is, that tries to automatically tune the client systems for their workload, right? So it's like so there's a script that you can use to invoke your application. So what the system will do, it will just change some random option in the BIOS, and then it will reboot the system and will run your application and will benchmark and then collect some statistics that you care about, and then it will reboot the machine again, and we'll flip another switch and we'll see if the performance improved. So this is sort of automatic tuning of your system for your application. So like tuning all the parameters in BIOS and everything. So like do you use something like that?
No, I'm that tool. I'm a human tool.
Okay.
But I wasn't aware of that tool. But how long has that tool been out?
I think I heard about it the last time probably a year ago, maybe. Yeah.
Okay, because it seems like lately there've been a lot of tools like that that's coming on the market. There's a company called Concert.io that it'll try a bunch of different compilation options. It'll try, well, I think one of the companies will compile your application with all the different compiler options that are available, and it'll do statistical analysis to figure out what is the ideal compiler option to use for your application. And there's another company that does it for kernel parameters or OS parameters, and I think it's called Granulate. So there's a lot of companies that's like that try to take the guesswork out of it, and they work. Once you get it going, I think it'll start running for like 24 hours or between 24 to 72 hours, and then it'll spit out the ideal configuration for your system. So yeah, right. That's something recent that's been like coming out lately. So I'm not surprised to hear that about the Intel product.
Yeah. So now Mark, let's talk about actually the networking layer. So this is really interesting to me, at least. So how do you optimize networking layer? So you said you bypass the kernel, right? Sometimes. So what are the other tricks that you have?
Well, the two main software products for bypassing the Linux network stack is Solarflare Open Onload and Mellanox VMA. Those are the two main ways, and their sockets based. So it allows you to, you basically do an LD preload of these libraries. So you don't really have to change your code. It's all sockets based, and you just preload these libraries, and they automatically bypass the kernel calls so that you call right through this user space library. And you get huge latency improvements. You can get even better latency improvement if you code like, so if people want to actually use an InfiniBand network to get the lowest latency possible, and then program with libIB verbs. That's when you're getting really, really low level. But you have to program, you have to actually do the TCP stack yourself. And I've worked for a firm where we did that. So that's an option. But those are some of the links that we go to avoid using the Linux kernel stack.
So you said you need to redo the TCP stack yourself. I'm trying to process what that means.
Well, the logic that the kernel would do for handling TCP segmentation and assembling a packet or receiving a packet, you would have to do that yourself if you decided to code directly to libIB verbs. Okay. So you get the lowest latency possible. And it sounds hard, but you can actually, if you decide what exactly it is that you need from the TCP stack, you can basically, you don't have to redo everything that TCP does, but just what you need in order to send an order and receive order acknowledgement from the exchange and a few other things. So you kind of like pare down what you need to do, and then you code to that. Now, again, not everybody does that. I mean, most firms don't do that. They'll just use a bypass product like Solarflare Open Onload or Mellanox VMA.
Cool. Yeah.
Also, as far as networks are concerned, I mean, most people will just use your regular run-of-the-mill switch. But we make sure we use very low latency switches. They have port-to-port latency in hundreds of nanoseconds, or you can use a layer 1 device. So there are a few companies that sell layer 1 devices that work on they call it a layer 1.5. It's basically an electrical level where they can switch packets at 5 nanoseconds port to port. So there's a lot that can be done to make sure that you're getting the lowest latency on your network. An example, so anybody want to research some of these vendors, one is Arista. They make Metamako devices or Metamux. There's another one called Exablaze. They make these layer 1 switching devices. So yeah, these are some of the vendors in that space that can give you port to port in 5 nanoseconds or less.
Oh wow. Sounds cool. Yeah. Great. Now, so let's switch to software stack. I think it should be even more interesting for folks here. So so what are the techniques to reduce latency and and control it and keep it within some threshold?
Well, the way, if you recall the way I explained how a typical trading system is set up, you're getting a whole bunch of market data constantly, right? And you're processing that market data and you're looking for signals. So that part of your code is running all the time. But on a relatively infrequent basis, you want to actually take an action based on a signal that you receive on that market data. So you got one half of your application that's constantly running, and then this other part of your code that can get actually cold, and then it can age out of the iCache. The problem with that is you want that infrequently executed code to be as fast as possible when you want to make take some kind of action in the market. So right when you need to actually send an order, you don't want at that point to incur an iCache miss or a Dcache miss. That's the worst possible time to do it, right? So
Right.
we employ techniques like cache warming, where we exercise that code on some kind of regular basis. Send a dummy order out that gets dropped right before it leaves the host, just to keep that instruction cache warm for when you actually want to send an order. Then you actually get an iCache and Dcache hit, and you get the lowest latency execution as possible. Also, something else that I noticed. So if you think about a lot of performance engineering books, they have these performance mantras that are pretty popular, where it's like, don't do it. Or number 2, do it, but don't do it again. Or number 3, do it less, or do it concurrently. All these kind of mantras that you can use when you're coding your application to get the best performance. So one of those performance mantras is, if you have to do something, take it off the critical path and do it concurrently. So you see that a lot, where a person, if there's some kind of heavy processing that needs to be done, but not necessarily in the critical path, then instead of doing it on that thread, on the critical path thread, you just do it on a background thread. The problem with that is, when you're in a multi-threaded application, even if you put on a background thread, the work that background thread is doing is not really that background after all, because the threads are sharing an address space. So some of the ways that you don't realize how that can come and bite you is that, let's say that you make sure on your critical path thread that you're not doing any memory allocation at all whatsoever. I mean, that's a given. Memory allocation is a latency killer.
All right.
So let's say that you're doing all kind of mallocs or new and delete or malloc and free on your background thread. Well, the problem with that is, any kind of call that you do that interacts with your shared address space, it takes a kernel lock. So for the address space, it's called the mmap semaphore. It's a read-write semaphore. Mm-hmm. So your critical path thread is not doing anything to the address space, but this background thread is. So if your background thread is doing something, it's taking a lock, and you need to do a page fault on your critical thread. Now that's a separate story. You shouldn't be page faulting either on your critical thread, but we can talk about that later. But let's say that you're doing something that's manipulating your address space on the background thread. So you have to take a write lock, but then you need to page fault on your critical thread that needs a read lock to that same lock. So you're inadvertently slowing down the progress of your critical path thread because of something you're doing on the background.
Right.
Or let's say that you're smart about it and you're not doing any kind of page faulting at runtime on your critical path thread. If you unmap, I'm sorry, say it again.
Yeah, just go ahead. Yeah.
Yeah, so let's say on your background thread, you're unmapping some address space because you malloced a large amount of space and you did some processing, and now you unmap it.
Okay.
The kernel has to send a TLB flush to every core that for every thread that's running a core on that process, because the kernel has to make sure that none of those other cores is going to reference that address space that was just unmapped. So it needs to flush the TLB on those cores that's actually using that address space. So these TLB flushes incur latency because it's going to take your thread off the core so it can do an interrupt service routine to service that TLB shoot down. So it can flush the TLB on all the cores involved with this multi-threaded application. So it's all these different ways that you think you're shunting something off to a background thread, but really that background thread can actually hinder your critical path thread.
That's interesting.
Yeah,
So
it's so many different things. It's like you're sharing so much that you don't realize you're sharing. And like, think about it. Would you ever think about someone checking like a performance monitoring tool, like Top or something like that, or some other kind of tool that looks at the proc file system and is checking how much memory your process is using? So let's say every minute it's checking.
Okay.
It's actually taking a lock when it needs to look and see how much memory your application is taking. It's taking that Nmap semaphore lock, just like anything else would. But this is like a harmless performance monitoring tool that can actually impact the latency of your running application.
Right.
So it's weird when you think about it, all the different ways that your latency can be impacted. I don't know if I explained that clearly enough.
Let's go back to this malloc example. So what is the proper way to allocate memory on the critical path? So you said well okay, so offloading into a background thread does not solve the problem, right?
Exactly. So you always pre-allocate memory at startup. You pre-allocate everything you need at startup, and then you work from that pool throughout the runtime.
Yeah, and you also touch the memory in order to prevent the page faults, right, in the runtime. That's
exactly
correct. Okay.
Exactly. So it's already pinned in memory. So you're not incurring any page fault. You're not doing any memory allocation or freeing at runtime. It's just all there, and then it goes. The memory goes away once the application is ended.
All right. Yeah, that seems like a lot of stuff you need to think about. So tell me, how do you find those things?
Okay, well, you can find like for instance, one of the first things I do if I determine that the issue is with an application is I use a certain list of tools right off the bat just to get a lay of the land. So I'll fire up perftop. I'll look at the proc interrupts file, which lets you know what interrupts are impacting a CPU. That's a really interesting one because I find a lot of performance issues can be found if you look at the /proc/interrupts file, because it breaks down every interrupt on the system and how many it's incurred on each individual CPU. And so it breaks down where there's a TLB shoot down, how many each core has received of those. It lets you know about if you're getting interrupts from a disk device or a network device. All that information is there, and you see the count since the machine has been up of interrupts that each core has received. So that is a very low impact way of finding out what's happening with your application on that server. So just by looking at that, not even profiling, you can get an idea of what you need to check further, just by looking at that file. But there's a whole bunch of different, not low level, but high level commands that you can run, like turbostat, that lets you know if you're incurring any system management interrupts. These are interrupts that the machine itself will send your core. And once an SMI operates, the operating system is not even aware of it. It just takes the operating system off all the cores on your system so it can run some firmware on the machine. So it's a really insidious type of interrupt because the OS is not even aware of it. So you have to make sure that you turn those off on the machine. But there's a command that you can run because there's an MSR that gets incremented every time an SMI operates. So the MSR is OX34. So you run this turbostat command and it lets you know if you're incurring any SMIs because you see that counter going up. But there's a bunch of different commands that you can run that's pretty unintrusive and doesn't impact the application as it's running, and it lets you know what's going on in the system. So that's one way of finding out without having to profile the application itself.
Interesting. Let me ask this question actually. So speaking about operating system, can the the entire HFT application work on a bare metal? Because I believe even from your perspective, even the operating system can be considered as overhead, right?
Yes.
So did anyone try that? Running on a bare metal?
Outside of an FPGA.
All right. Yeah.
I'm not
Outside
aware.
of FPGA.
I'm not aware. I've heard of other things it's not like running a bare metal, but I've heard about other projects where you're pretty much running on a very, very thin kernel. Like I've heard this project called Include OS.
Right.
But I haven't tried it. I don't know how much it could help or how much work it is and actually get a full trading system running on Include OS. But I've heard about things like that where you can get your application to run on a very, very thin operating system so that you have far less to do when it comes to kernel tuning. But I haven't tried that.
Yeah, that would be interesting. So Mark, so let's talk about cache allocating. So do you use any techniques like that, like when you allocate the certain amount of cache for your hardware thread?
Yes, I've used that in the past. Not at every firm. I've used it where it counted, where we saw a benefit. More often than cache allocation, we've used it used to be called cluster on die, but then the newer chips called sub-NUMA clustering, which you get the benefit of that sort of because you can split one CPU into two different CPUs, basically two different NUMA nodes, and you get an effective isolation of the LLC that way. So that's an easier way of getting that kind of LLC separation, so you don't suffer from the noisy neighbor situation. But cache allocation technology is one way of doing it, so you can have more a finer grain way of separating the LLC cache and dedicating it to one set of cores, and have another part of the LLC dedicated to another set of cores. So the memory bandwidth enforcement is another one that you can use. So if you have, again, like a background thread that's doing a whole lot of the housekeeping work, and maybe that background thread uses a lot of memory, you don't want that memory corrupting you don't want that background thread using too much of the memory bandwidth, and that ends up affecting the latency that the critical thread incurs once it goes to that memory controller to get access. I mean, not that the critical thread would actually be using a whole lot of bandwidth, but it's just a contention. You have more requests going to the memory controller. That's more requests that it has to juggle. So you can limit the amount of bandwidth that this background thread is using the memory bandwidth enforcement that's available on Intel chips.
Right. Yeah, that's interesting. Any other tricks that were missed or you want to talk about regarding software?
Some of the things that I see more often than not when it comes to the software itself is false sharing. And everybody knows about false sharing. It's this, you talk about it in the book. There's been a lot of articles written about it. I've used perf C2C, which is perf cache to cache, to detect false sharing lines. It's fairly simple to resolve once you find out what's the cause of the cache lining, false cache issue. That's one of the things I see most often as far as software is concerned, because for the most part, in HFT, everyone knows about the fact that it all starts with optimal data structure selection. So very rarely do you have to go and say, "Oh, wow, we're doing pointer tracing here. Let's use something that's more friendly to the cache." You just rarely see that. So more often than not, that in my experience, it's been troubleshooting where you're running into some kind of false sharing.
Sure. Yeah. Can you talk about what languages are used in HFT? Like for example, so I saw that even like garbage collecting languages are like Java are used in HFT space. So can you comment on on language selection for the application?
Yeah, you can get into a lot of religious battles when it comes to
Oh.
that. And so, I try to avoid getting into those discussions, but what I'll say is this: the successful firms that I know that actually use Java, they either used Azul Zing, which is a product that uses a JVM based on the C4 collector that basically is a pauseless garbage collector. So you're not suffering the garbage the garbage collection pauses. That costs money, of course. Or some of the other firms, they write Java in a way that almost it doesn't even look like Java anymore. And that's the way you get away from the garbage collection, and then you don't incur that kind of latency. Those are the two methods that I've seen for successful Java firms. But for low latency Java, it's like there's some kind of module called unsafe, so that you can get you can get the kind of alignment that you want from your data structures, and you can kind of bypass what the garbage collector wants to do with things. I'm not a Java expert, but this is what I've seen as far as successful firms. But most firms is they're using some kind of commercial JVM like Azul Zing.
Mm-hmm. Makes sense. What about Python? Is Python used for HFT?
Python is a lot of firms use Python for backtesting things. So I mean, there's a lot of data science libraries available for Python. So whereas you probably have a lot of quants in the past who would use R or RStudio, you see a lot of them kind of changing over to Python in the past 5 years or so. So yeah, Python is heavily used, but nowhere near it doesn't get anywhere near the critical path for a trading application. Not at all.
Right. Or maybe people just prototype in Python and then they rewrite it in C++. Right.
Sure. You can prototype an application in Python. I haven't worked at a firm where it was done in that way, but that's a possibility.
Right. Okay. That makes sense. So Mark, we already actually talked about briefly, but what is your approach to performance tuning? Like, what tools do you use? Like how do you approach performance engineering in general?
Well, I think it's important to have proper metrics, and so I just think it's great to have network tapping, so that you can actually get precise timestamps for everything that happens along the path from ingress to egress. So that having that kind of granular data in a centralized location, it helps you pinpoint exactly where you need to devote your efforts. I mean, you can be buffering in a switch or dropping at the switch and you don't know. It's you got to have that kind of telemetry to know where you need to spend that time. But let's say that you get that telemetry and then you decide it's at the machine level where the trading application is running. My method is I like to start with high level tools to begin with to find some low hanging fruit, just to make sure, because the thing is with a trading application, you want to make sure I mean, the trading application is like a race car, and you want to make sure that it's not running on some kind of cobblestone road. You want to make sure that the road is as smooth as possible so it can get up to the best speed available. So to smooth out the cobblestone road, you want to make sure that the server itself is not interrupting you or not down throttling you for power or thermal sake. You want to make sure the OS is not interrupting you when it doesn't need to. And this is, if you upgrade the OS, there's so many surprises that come with each new kernel release. There'll be a new kernel thread that you didn't know was instituted that does something that's supposed to be helpful for throughput, but it's hurting you latency wise. So you have to be vigilant with that. But the good thing about it is there are high level tools that you can use that where you'll be able to see that, and it'll give you an indication of whether you need to dig deeper with maybe some kind of kernel tracing tool like ftrace or eBPF, which Brendan Gregg writes a lot about on his blog and in various books he's published. So yeah, I like to start off with high level tools. That gives me a lot of information to decide where I need to go from there. As far as code profiling, I'm a big fan of perf. So I'll use perf record. For multi-threaded applications, I'll use vtune or cause, which I wrote about in your book, the cause profiler. Cause is instrumental for multi-threaded applications because typically when people use a profiler, they use it on a single threaded application, and then it's pretty obvious what's causing your system to slow down because it shows up at the top. This is the function that's using all your CPU. So if you tune this one and it uses less CPU, it's going to run faster. But that's not necessarily the case with parallel or multi-threaded applications. You can have some thread that's just constantly polling the network card for new packets, but it's not really doing anything. It's not contributing to the latency that you incur when you're trying to read a market data packet and then respond by sending a trade to an exchange. It could be something else down a path that barely ever executes. But when you fire up a profiler, the thread that's spinning looking for network packets, that shows up at the top. So that's sending you on a false chase and a wild goose chase. So cause is an application that can actually target. It can actually show you where you're spending your time or what's actually going to give you the biggest bang for your buck. Intel actually has a product, well, not a product, but it has a facility called Processor Trace. And in their product, Intel vTune, it can tap into the processor trace capabilities of the chip, and it can help you detect anomalies. That's something that is hard to find with a profiler because when you profile an application, it's taking samples. So let's say that this anomaly happens, it's intermittent, and when an anomaly happens, let's say that your tick to trade latency is typically 3 microseconds, but then every now and then it balloons up to 30 microseconds. A sampling profiler may never catch something like that because it happens in such a short time scale. Whereas with processor trace, you can find those anomalies and you can find out what's the actual source of that anomaly. So yeah, there's a lot of tools that are available now that weren't available before in the early days of algorithmic trading.
Right. Yeah. So I actually love processor traces, but I should say that for most of my work, processor traces is definitely an overkill. But have you used processor trace and really found some interesting issue using this capability?
Yes, I used it when it was first experimental. So I think I talked to you about this, but when I was at another firm, Intel flew me out to their headquarters to show me this new experimental feature that they were thinking about putting into vTune, and they wanted to know what I thought about it. And so they gave a presentation. I thought it was a godsend, and it was something I thought the industry needed. So when I flew back to Chicago, they gave me the eval copy of VTune with that feature available. And I actually used it to for one specific application to find a source of an anomaly. But I had a temporary license, so I use it on this specific case. It wasn't on a mission critical application, but I wanted to test it to see if it actually worked. And so it was so slick the way it worked. I was like, oh my God, this is going to be great. But I haven't had a chance to use it in production because once my license expired, like I said, it was an experimental feature. So I was waiting for it to become GA, and it had been a long time. I was like, okay, when is this going to be general release? And I even sent you an email message. I was like, hey man, do you know anything about this? Because I know you're a VTune expert. I was like, do you know anything about this? Like, when is this going to be generally available so I can like actually make use of it? And then I actually found a cookbook on Intel's site about that feature. I was like, oh, okay, it is generally available. But I didn't know about it because the firm I work at now, they don't have Intel VTune in-house the way I had at this other firm. So I plan to use it now, definitely.
I see. Yeah, that's great. So yeah, so and actually, it's a little bit sad, that the adoption of processor traces is going pretty much slowly. I would say. The last time I actually used the processor traces was more than a year and a half ago, probably, and I used it in Linux Perf, and it was so slow that you can barely use it for anything. You can barely doing anything useful with it. So it was working so slow that yeah, but I hope that now it will get better and it will be more adopted.
Yeah, it was really slow on Broadwell. Definitely, it was really
Yeah.
slow.
Yeah. Okay. So Mark, any performance debugging stories that you can tell?
One interesting one. I'm actually going to write a blog about it, but there was it goes back to this whole background thread thing where you don't want it on a critical path, so you put it on, you fire up a new thread and put it on a background thread. So there was this one options trading system where it did a lot of heavy disk IO on one particular background thread. It was pretty heavy, the amount of IO that it needed to save. So they of course they had to put it off the critical path. But this was a separate trade. So at this particular company, all the different trading teams, there were like 30 plus trading teams that did their own strategies. So, I belong to a centralized performance architecture and R&D team. So, at any one given time, we're not aware of all the strategies that a team is using. So we had no idea about this new trading firm and this new trading team and what it was doing or what the case is. All we know is that they reached out to us and said that, hey, every now and then we're incurring this 10 plus millisecond latency on our trading thread. So when anyone says something about milliseconds, I automatically think of disk IO. It's like it's good to have a mental model of latency numbers because it gives you a kind of lay of the land of a good usual suspects to target first. So of course, when I looked at the application or looked at the thread, they weren't doing any IO on that critical thread, just like they professed. So I looked at /proc/interrupts, just like I told you before. I always like to do these high level overview of the system before delving into any kind of profiling. And sure enough, I saw some anomaly in that file. It showed that there were a bunch of function call interrupts that were being sent to the core on which this critical thread was running. So every other core on the system had a very low number of function call interrupts that were being sent to it, but the core in question had tons of it. So now I'm like, okay, what is this? So it required some kernel stack tracing to find out, okay, what's calling these function call interrupts and what's the stack trace that's sending it. And it turned out that the block layer, the block IO layer of the kernel. So when you send a whole lot of block requests or IO requests to a disk device, it would go to this block queue, and the block queue would do all kind of, it will look at all the requests that's coming to the block queue, and it will look for some that maybe I can coalesce some, maybe I can send this one before I send this one. It would do all this kind of reordering so you get the best use of the disk device. Once the IO is complete, then it would need to process, it would need to release all the memory that block IO request was using. It needs to free that up again so that the next block IO request has memory available to send something to the device. So that has to run somewhere. The way it decides where it needs to run is it says, if the person who sent me this block IO request is running on a certain socket, I'm going to send this request completion work to the first core on that socket, so it can get the best cache performance, because I'm sending it always to the same core on the socket. It won't send it to the thread that actually sent the block IO request by default. It's going to send it to the first core on that socket where that background thread was. And where was the critical path thread running?
Of course,
on the
core
first
number
core.
0.
Exactly.
So
it's crazy. Like these are just one of those aspects where some kind of background process can actually bite you in the butt. And so there's a kernel parameter that you can set that prevents it from doing that. But yeah.
That's amazing. That's amazing.
Think about that. 16 full milliseconds. And it was happening on an intermittent basis. So it was just driving them crazy.
Yeah. That's unfortunate choice, of pinning your thread to core 0.
Exactly. And it's a funny thing because nowadays, I have a colleague who still works there. He says that new teams, they're so scared of the first core now. And this is over a decade ago. But people are so scared of the first core that they reserve the first core for housekeeping, and all the latency sensitive threads always go on any other core but the first core of a socket.
Oh, that's funny. Oh, interesting. Okay. So Mark, any other stories you can tell? I would actually love to read about this on your blog. So
yeah, I'm gonna write it in another blog for July. I'm gonna try to write a blog entry for once every month. So one cool thing about working in high frequency trading is that a lot of these firms, they're signed on for the early access program with a lot of these chip manufacturers. So I will be able to get chips before they're generally available and then test them out so that I would be able to let the CTO know if it's worth trying to buy a bunch of these chips to replace our current chips before it becomes generally available. So I have an interesting story about when Haswell was the dominant CPU, or the current CPU, and then Broadwell was coming out. So I was able to get an early access Broadwell chip. And one of the issues that happens with Intel chips back in the day is when they had inclusive caches. So with an inclusive LLC, if you have two threads running on a CPU on a socket, of course, they're going to share the LLC. So if you have one of these threads, it's using a lot of memory. So it's consuming a lot of the LLC, while another one, it barely uses the LLC. So it's not like it's really suffering from the fact that it doesn't have a lot of LLC available because it's getting all of its cash hits from the L1. So you should think that this is not a big problem. But the problem with inclusive caches is everything that's in the L1 and L2 of every core has to be in the L3 for an inclusive cache. So what that means is if this other thread is using so much memory that it pushes a line that's in your thread's L1, it pushes that cache line out of the LLC. By law of inclusive caches, it also has to kick it out of the L1. So you would get these crazy scenarios where just because you're using an inclusive cache, it's kicking things out of your L1 because of this noisy neighbor situation. So the story was that Broadwell was going to introduce some feature called query-based selection, whereby before the LLC would decide what line to kick out of its cache because it needs more space, it would make an inquiry to the L1 of the core that it's about to evict, and it'll say, "Hey, are you using this cache line in your L1?" And then the L1 can respond back, "Yes, I'm still hotly using that cache. Choose something else." And so this was going to be a way that was going to stop that whole noisy neighbor situation with inclusive caches. So I was anxious to try that. I had a test harness set up to test it out. It would always on the Haswell, I was able to reproduce this pathology over and over. And so once I got the Broadwell, if query-based selection worked as planned, then it would be resolved. Of course, I got the early access, ran the harness, and I got the same pathology. So I'm like, okay, wait a minute, what's going on? It's like, is this something wrong with my harness? And so going back and forth with Intel Engineering, they finally told me, so, oh yeah. I know we told you when we flew you out for the roundtable that we're going to incorporate query-based selection, but we decided not to at the very last minute. So I wasted all this time testing out query-based selection, and they had disabled it right before sending it the early access to us because they ran into some kind of issue with it. So yeah, I thought that was a funny story, but yeah, I wasted a lot of time with that. But but that's one kind of cool thing about working for these HFT firms, because they'll get a lot of access with the chip vendors themselves that you probably wouldn't have at another company.
Yeah, that's funny. That's really funny. So Mark, so you started your own consultancy firm. So tell us, like what was the motivation and how's it going for you?
Well, I've always wanted to have my own consultancy because I've been doing this for a while and I have a good feel for it. And then also I noticed something in the industry. Smaller trading firms, they typically don't have the resources to have a full-time performance engineer. It's usually the HFT firms that have 200 or more people. Those are the type of people that usually have a dedicated performance engineering team or person. But these smaller firms that are like, they have 20 people to maybe 50 people, they really desperately need someone to look at their performance, but they can't hire someone on a regular basis. They just need someone to do like a 3-month project here or there. So I thought that my consultancy can fill that need in the HFT and fintech industry. So yeah, that was the motivation for it. But I'm not actively doing it now because, as you know, I work at WH Trading, so I lead the performance efforts there. But I do want to eventually do that. And so right now, I just launched the website because, as you were encouraging me to do, you said, "Hey man, you should start a blog." So I was like, "Well, if I'm going to start a blog, I'm going to start it under my company name." So that's why I did it. You know, I'm not just going to start any blog and put it anywhere. I said I might as well fire up the company website now and then put the blog on the website. And for anybody wondering why I call it Jab Perf, it's because I have an amateur boxing background, and the jab is the fastest strike. It's point A to point B. It's straight. It has no, bells or whistles to it. It just goes from point A to point B. So with a jab being the fastest thing, I associate that with performance. I love boxing. I love performance tuning. So I called it jab perf.
Great. Cool. Well, best of luck with your with your new gig. And just so before we let you go, Mark, any advice for books, for any podcasts, any studies, any research, whatever.
You had a guest on a month ago, Daniel Lemire. He sent out a link with a list of performance podcasts and websites that he looks at. Those are generally the ones that I look at. Like the usual suspect, like Travis Downs. You have a good blog. The usual suspects. Those are kind of the ones that I look at. Now, myself being on the system side as well as the C++ side, I look at certain kernel performance type of blogs myself. So Brendan Gregg's is a great blog to follow, which is basically, I think it's brendangregg.com or brendangregg.org. It's one of the two. But he has a really good blog on tracing, using some of the kernel tracing tools to find performance issues. I highly recommend that. Or his books. He has a systems performance book and a BPF performance tools book. If you want to learn more about that kind of performance tuning outside of C++.
Cool. Great. Well, Mark, it's been great talking to you today. So many insights about high frequency trading and performance, and
I'm surprised there were no questions. That's a first.
Yeah. Folks are quiet today. All right. Thanks, Mark, and I love to see you join us next time. And to everyone else in the room, see you in 2 weeks, and happy performance tuning.
Have a good one.
Thank you. Bye.